Welcome back. In this lecture, we are going to discuss on wave nature of a particle. After Planck's hypothesis, it was theoretically and experimentally established that an electromagnetic wave, like light, shows its particle nature in some of the phenomena like photoelectric effect and Compton effect. That means any electromagnetic wave can show its wave nature in some phenomena like reflection, refraction, interference, diffraction, dispersion, and in some other phenomena like photoelectric effect and Compton effect, it shows its particle nature. And it was theoretically and experimentally verified by scientists like Einstein, Compton, Davison, and German. Then Louis de Broglie thought, is it possible that a particle like an electron may shows its wave nature? And de Broglie hypothesis was established, and according to de Broglie hypothesis, whenever a particle is in motion, a wave called de Broglie wave or matter wave or pilot wave is associated with that particle. If momentum of that particle is p, then the wavelength of the wave associated with that particle can be estimated as the ratio of Planck's constant to the momentum. Since momentum can be expressed as the product of mass and velocity, therefore the wavelength of the matter wave can be written as lambda equals to h by p or h by mv, h being the Planck constant. So for this de Broglie hypothesis, there is only one restriction, and that is the particle must be in motion. So whenever the particle is in motion, then theoretically a wave is always associated with that particle. Whether the particle is tiny or large, whether it has charge or is neutral, the wave will be associated with it. And we call that wave as de Broglie wave or matter wave or pilot wave, as it is assumed that this wave is actually guiding the particle. We can establish this de Broglie hypothesis from well established laws like de Broglie hypothesis can be verified, can be proved from well known Bohr's theory. And we know, according to Bohr theory, within an atom, electron rotates around the nucleus in several particular orbits, some allowed orbits. So let us consider an electron which traveling along its allowed orbit. Since its motion is considered to be stable, every event after each revolution around the nucleus is repeated precisely as before. Therefore, if the electron is at a point of the orbit at any instant, say the electron is at this point at any instant, then it would be at that same point after each revolution. So when it comes back after one rotation, it will be exactly at this position. Therefore, if it is assumed that a wave is associated with that electron, then the wave must have the same form at that point after any revolution. That means if the crest of the wave, if the crest of the wave, if the crest of the wave appears at that point, then it would always be the crest after each revolution. So after each revolution, it is the crest that should be here. Otherwise, the wave and the particle cannot be associated with each other. To provide this consistency, the orbit must accommodate an integral number of waves associated with that electron. Therefore, if Rn if Rn be the radius of nth Bohr orbit, so if we assume this is nth Bohr orbit, its radius is Rn, and lambda be the wavelength of the associated wave, then the circumference 2 pi Rn must accommodate an integral number of waves of wavelength lambda. So from that, the radius Rn can be written as n lambda by 2 pi. Now, according to Bohr theory, For an electron rotating around the nucleus in the allowed orbit, the angular momentum of the electron is an integral multiple of h by 2 pi. That means the angular momentum mvrn would be equal to integral multiple of h by 2 pi. When Rn is replaced by n lambda by 2 pi in the equation, then it will be mv n lambda by 2 pi equals to nh by 2 pi. So we can cancel these quantities. So and mv is nothing but the momentum of the particle. Therefore, p into lambda is h. In other words, lambda equals to h by p, the mathematical form of de Broglie hypothesis. So from both theory, we can easily establish de Broglie hypothesis mathematically. Similarly, we can establish the mathematical form of de Broglie hypothesis from the energy of a photon. From the expression of relativistic energy, the total energy can be written as square root of p square c square plus m naught square c. Therefore, where p is the momentum and m naught is the rest mass. Now, if we consider a photon, then rest mass of photon is 0. So, rest mass of photon is 0. Therefore, energy equals to root over p square c square, that is pc. And we know that energy of a photon is equal to hc by lambda. So, if we use these two facts, then we get hc by lambda equal to pc. Cc cancel out, giving lambda equals to h by p. Again, the mathematical form of de Broglie hypothesis. So, the de Broglie hypothesis can be established from any other well-known or well-established laws also. And if the momentum of the particle is known, then the wavelength associated with that wave can be estimated. So, if we know the momentum p, then we can find out the wavelength of the de Broglie wave. But instead of momentum, if energy, say kinetic energy of the particle is known, or if the accelerating potential is supplied and we need to estimate the wavelength of the matter wave, that can also be established. So we can find out the relation either through non-relativistic approach or through relativistic approach. If we assume the non-relativistic approach first, then the kinetic energy of the particle in motion can be represented by its momentum as kinetic energy equal to half mv square. The momentum, in terms of momentum, kinetic energy can be written as p square by 2m. From that, p can be written as root over twice m ek. Since from de Broglie hypothesis we know lambda equals to h by p, we can replace p in terms of kinetic energy. So lambda will be h by root twice m ek. So if we know the kinetic energy of the particle instead of its momentum, we can directly estimate the wavelength associated. Instead of kinetic energy, if we know the accelerating potential, then that accelerating potential actually gives the required potential energy, which is converted into the kinetic energy of the electron. Therefore, kinetic energy ek can be written as ev, and if we replace the kinetic energy in this equation, then lambda comes out to be h by root over twice m ev. Now, if we consider the particle as electron, then all the quantities here except V are known for electron. We know Planck's constant, mass of electron and charge of electron are also known. So if we put those values in lambda, then the wavelength of the de Broglie wave comes out to be 1.227 into 10 to the power minus 9 by root V in meter. In angstrom, the value will be 12.27 by root V. Therefore, if we know the accelerating potential supplied to an electron, if the accelerating potential supplied to the electron is known, that is V is known, then from this formula we can directly estimate the wavelength of the matter wave or de Broglie wave. So this is the form we get if we use the non-relativistic or normal Newtonian mechanics. If we use the relativistic approach, then the total energy of the particle is just the sum of its kinetic energy and rest mass energy. Is the sum of kinetic energy and rest mass energy, which is m naught c square, m naught being the rest mass of the particle. That means the mass of the particle when the particle is at rest. So if we square both sides, it will be like this. Again, from relativistic mechanics, we know that total energy E can be written in terms of momentum and rest mass m naught by E square equal to P square C square plus m naught square C to the 4. So instead of E square, if we write the value in terms of momentum and m naught, then left hand side can be written in this way. Therefore, these two terms cancel out, leaving Pc equal to root over this quantity. Since wavelength is h by p, you can write hc by pc by multiplying velocity of light in free space on numerator and denominator and replacing pc with the quantity that we have estimated. The wavelength of the de Broglie wave can be written as hc by root over ek into ek plus twice m naught c square. Again, instead of the kinetic energy supplied to the kinetic energy of the particle, if the accelerating potential supplied to the particle is known, then we can write Ek in terms of accelerating potential as Ek equals to Ev. So the wavelength of the matter wave will be this. So if we know the supplied accelerating potential, then with the help of this formula, we can easily estimate the wavelength of the matter wave. As for example, say in this numerical, it says that what is the de Broglie wavelength of an electron which has been accelerated from rest through a potential difference of 100 volt. So accelerating potential is supplied, and we need to estimate the wavelength of the matter wave associated with an electron. So if we use the formula obtained from relativistic approach, then lambda will be this. Here all the quantities are known. H, the Planck's constant, is 6.626 10 to the minus 34 joule second. Velocity of light in free space is known as 3 into 10 to the power 8 meter per second. Charge of electron is known. V is supplied in the question as 100 volt. Rest mass of the electron is known as 9.11 into 10 to the power minus 31 kg. So if we put all these values, sorry, this will be 9 only. Then the lambda is estimated to be 1.227 into 10 to the power minus 10 meter. That is 1.227 angstrom. So if we know the potential difference or accelerating potential, then we can easily estimate the de Broglie wavelength if some other quantities like mass, charge of the particles are known. In problem 2, it says, to what velocity must we accelerate a particle so that its Compton wavelength is equal to the de Broglie wavelength? So according to the question, Compton wavelength, say lambda c, is equal to de Broglie wavelength, say lambda. So lambda equals to lambda c. Now we know that de Broglie wavelength lambda can be written as h by p, whereas Compton wavelength can be represented as h by m naught c, m naught being the rest mass of that particle. So from that, we can say that since numerators are same in both left hand side and right hand side, so P equals to m dot C, and P means momentum is product of mass and velocity. So P equal to mv. Now from relativistic mechanics, we know that mass of a particle moving with a velocity v is m naught by root over 1 minus v square by c square. So instead of m, we can write the relativistic mass as this, and in doing so, m naught is cancelled out from both the sides, so that 1 minus v square by c square equals to v square by c square. So from that, we can say v square equal to c square by 2, or velocity of that particle equals to 0.707 into c. That is 0.707 into 3 into 10 to the power 8 meter per second. So that will be the de Broglie wavelength of the particle for which Compton wavelength is same as the de Broglie wavelength.